In this video, I'm going to be talking about how to pick out every piece of information from a graph, particularly a motion graph. So the one we're taking a look at right now is an x versus t graph, x meaning position, and then t for time. So if we take a look at all of these different things, the title, the y-intercept, data points, slope, and area, we can pull out a lot of information about an object from taking a look at the graph and being able to analyze it in a specific way. Okay, so let's start off with the title. So with the title, it is always titled the dependent variable versus the independent variable. So what that means is, although I don't know the object involved in the experiment or that the graph is representing, I know that my dependent variable is position and that my independent variable is time. And if you know what independent and dependent variable are, you basically know the entire setup of the experiment or how the data was collected, which means that they were controlling time and letting it grow by, we'll say, maybe 1 second at a time, and then measuring the distance that it traveled or measuring the position of where it was at every second that that object moved along. Okay, so that's the title. Number 2, the y-intercept. The y-intercept is right over here. It is basically where the line bumps into the y-axis where x is 0. So x as in the x variable, so not x as in the position. So when x is 0, we really mean where the time equals 0 seconds. So at time equals 0 seconds, my y-intercept is 1 meter. And that 1 meter for this particular graph, you would call it xi or xo, okay, which means initial position. So the I for initial and then x naught, which also means initial position. Whatever the case is, it is wherever the object is starting out at. Number 3, the data points. So if you take a look at any particular data point, you're basically looking at a single point in the graph. That just tells you the specific position of where it's at. Okay, a lot of times you might call that an XF, the final position, but the final doesn't necessarily have to be right over here. The final could be kind of like wherever you cap it. You could say my final position is here, my final position is here. Whatever the case is, if you're taking a look at any particular data point, it is the position of the object at a specific time. Another thing that you can do with data points is you can also find a delta X. Okay, delta X is the displacement. The displacement is how far it has been displaced from an original position. So if you take a final position minus initial position, you can find out how far the object has moved. So in this particular case, if you take a look at the position, it looks like over here, it's at about 4 meters. If we take a look across over here, and then at 3 seconds, it is at about 3 meters. So then technically what you do is you would take 4 meters minus 3 meters, and that's equivalent to 1 meter. So that is how you would find a delta X, a change in position for, you could usually, what you would do that from probably 0 to 7 seconds. So you can get an idea of how far the position has changed from the very beginning to the end. Number 4, the slope, which is a very common one. The slope is always the change in y variable over the change in the x variable. So our y variable for this one is x, which is position. So it is our change in position over our change in time, because our x variable is time. Okay, so how much something moves in a particular amount of time is actually the velocity. Okay, so if we find the slope, the rate at which the position changed per a certain amount of time, we call that the velocity. So in this case, it goes from, it starts at 5 meters for the final position. So 5 meters minus the initial position, which is 1, over, and then technically it'd be like 7 seconds minus 0 seconds. So to find the change in anything, it's always the final minus initial. So final position minus initial position, and then final time minus initial time. So then it would be 5 minus 1 equals 4, and then 7 minus 0 equals 7. So it's 4 over 7. Okay, and you can put that into your calculator and make that a decimal if you would like. Okay, so that would be your exact velocity. Number 5 is finding the area. So the area is oftentimes referred to as the area underneath the curve. The curve doesn't necessarily mean the line is curved. It just means like the line that is representing your data. So you can just call this the curve, although it's not physically curved. Okay, the area would be the space underneath it. Okay, and for some graphs that does represent something, and if you were to find the area of part of it, it would be some form of taking a position times a time. And then if you take some kind of position times a time, that doesn't actually give you anything at all. So when you take the area between your curve and the x-axis, sometimes it will give you a pertinent piece of information. For a position versus time graph, it does not. Okay, so let's move over to taking a look at a velocity versus time graph. So for our velocity versus time graph, we're going to run through these 5 things and then see what type of information it gives us. The title is still going to be similar to where it's the dependent variable versus the independent variable. So the velocity is the thing that we are measuring the results of, and then the time is the thing that we are manipulating and controlling. So for number 2, the y-intercept is right over here, and that would be 2 meters per second, and that would be known as VI or V naught. Okay, which is the starting velocity, because it is the velocity when time equals 0. Number 3, if you're taking a look at the data points, again, it's just going to tell you a very specific velocity at a specific time. So it will give you the velocity at any specific spot, which you could call an instantaneous velocity, or you could possibly call it a VF. Whatever the case is, it is how fast they are going at a specific time. Now, if you wanted to find a delta V, just like as I spoke about before, you take a final data point and you subtract an initial data point, whichever that may be. So if you're trying to find the delta V for, this little section over here, you could say at 10 seconds, it is going at 8 meters per second. So 8 meters per second. And then from over here, it is going 4 meters per second. Okay, therefore, the change in velocity is 4 meters per second from the 4-second to the 10-second mark. Okay, number 4, finding the slope. So the slope, as I said before, is the change in the y variable over the change in x. And if you take a look at that for this graph, it is the change in velocity per time. So you're taking a look at how fast the velocity increases or possibly decreases within a specific period of time, which is known as the acceleration. So if we were to find the slope of the entire graph, we would take the final velocity, which is 10. Okay, so if we take this final point over here and then track it back over here, it looks like it's at about 10, minus the initial velocity, which we already said was 2. So minus 2 meters per second. And then we have the total time, which is technically 14 seconds minus 0 seconds, which is obviously still 14 seconds. So 10 minus 2 is 8. 8 meters per second. And at the bottom, it is 14 meters per second. So in the end, our acceleration can be expressed as 4 over 7 meters per second squared, or you could do 4 divided by 7 and then go ahead and round off that decimal. Number 5, the area. So finding the area, it would be all of the area underneath this line, so between the line and the x-axis. So because the velocity can be negative, I won't always say it's underneath the line because it could potentially be over here, and then your area would be shaded in over here. So then in that case, the area would actually be above the line. Okay, but a common term is area underneath the curve, but what people really mean is the area between your line of data and the x-axis. Okay, so for this one, if we're finding the area, it is basically multiplying the velocity times the time. And if you take the velocity times the time, it will actually give you the delta x. Okay, so if you find out how many meters per second they are going times the amount of seconds, it will tell you how many meters that thing has traveled. Now, if I want to find the area for this, what I'm going to do is I'm going to split it right over here. I'll go ahead and split it in a different color. Okay, and then that way I could find the area of two things, find an area of a rectangle, and then find the area of a triangle. So if we're just doing base times height for this rectangle, it goes up 2 and then over 14. 2 times 14 is 28. Okay, so the delta x for the purple chunk is 28 meters. Now for the triangle, it is 1/2 base times height. So 1/2, the base is still 14. And the height isn't 10 though, because it goes from 2 up to 10. So 2 up to 10 is 8. So then 1/2 times 14 is 7, and then 7 times 8 is 56. So 56 meters is the delta x for the top part. Okay, and we can go ahead and add these two together, and that's going to give us our total delta x, 84. Okay, so if you're lucky enough, you may just have a rectangle to find the area of, or you might just have a triangle. So in this case over here, I had to find the area of a rectangle and a triangle, which isn't terribly difficult. You just want to make sure you slice it up to make that rectangle and that triangle so that you don't make the problem any more complicated than it actually is. Okay, so that covers everything for velocity versus time graph. So now let's head over to the third one, an acceleration versus time graph. So for the last one, we have an acceleration versus time graph, and the acceleration is our dependent variable, and then our time is still our independent variable. So we are controlling the time, letting the time go up, and then seeing what happens to the acceleration as time elapses. Now for the y-intercept, again, it's like that initial value, and the initial value here is it goes 1, 2, 3, 4, 5 up. So the initial value right here is 2. So it is 2 meters per second squared. That is what we would call the acceleration, and we'll call it AI for the initial acceleration. But for this one, it is a constant or uniform acceleration. So there really is no change in acceleration. So you normally don't distinguish whether it's the initial or the final. Okay, for number 3, the data points is nothing too special, especially since we have uniform acceleration, which is very common. So if we take a look at the acceleration at any point, it's just going to give us 2 meters per second squared, and there wouldn't be any change in acceleration. So if you were to find any change in acceleration, it would be 0 for this graph because it stays constant. Number 4, if you were to find the slope, it is the change in acceleration per time, which is known as jerk. So it is the rate at which you are increasing or decreasing your acceleration. Okay, so for this one, it doesn't have any change in acceleration. So it'd be 0 divided by that 7 seconds, which would still give you which would give you 0 meters per second cubed, because it's how many meters per second squared have changed per second. So for the final one, we have the area. So the area for this one works out pretty nicely because it's basically just a rectangle. So it goes up 2 and over 7. So the area is going to be 14. Okay, now is that 14 going to be useful to us? Now, if we take the rate that it is changing its velocity times the time, that will give us the change in velocity. Okay, so if we take the rate that velocity is changing as meters per second squared times something in seconds, that actually causes one of the units of seconds to be canceled out, and we have something in meters per second, and that 14 meters per second is the change in velocity. All right, so there it is. To sum things up, if you take a look at any graph, especially some sort of motion graph, if you take a look at the title, you can see what the dependent and independent variable is. If you take a look at the y-intercept, you basically find some kind of starting value of whatever is displayed on the y-axis. Could be position, velocity, or acceleration. If you're taking a look at data points, that will give you specific values at very specific times, and you can find changes in those values too. Changes are always some form of doing a final minus initial value. Number 4, the slope is going to be very important in lots of cases, and the slope is telling you the rate of change. So it's the rate of change of the y variable, so how quickly the y variable is changing in respect to the x variable. And for this one, the change in acceleration over time is jerk, and that comes out to 0 meters per second cubed. But for a lot of the other ones, you'll find something maybe a little bit more pertinent, like the acceleration or the velocity. And number 5, the area is a cool trick you can use to find the change in a certain value. So when you multiply the y variable times the x variable, and you basically find the area of some sort of rectangle or triangle or both, then that area may give you some information about the change in velocity or change in position. So I hope that was helpful in helping you understand and break down every part of a motion graph. Thank you for watching and listening.